All right, this is on a new approach to teaching of proportion. And proportion is a very interesting subject. It's also very, very big because we use proportion in many aspects of our lives. I mean, this picture, for example, um, has proportion in it, of course, but it as a visual image, it gives us the sense of space. So the that one elephant is a long way in the distance, and that gives a sense of space. So we're going to look at the Vedic approach to proportion, and in this webinar, I'll be looking at what proportion means, at uh, the examples in the Vedic Maths book by Tirtha, a rule for ratio equations with examples, similarity. There's one problem on similarity. Examples that we find in the world of design. Now, in Vedic Maths, the relevant sutra or sub-sutra is Anurupyena, which means proportionately. And if you look at the Sanskrit literally means by means of that which has the same form. So rupa is the word for form, and anu is same, and the ending ena means by means of. So by means of the same form. In English, the word proportion is used in different ways, and they're fairly. Some of them are fairly loose. So I've put some examples here just to illustrate the different ways in which proportion is used in language. And this is not always the same as the mathematical meaning. So if we have a look at these four sentences, children make up a large proportion of the world's population. The proportion of women to men at my college was about 5 to 1. The level of crime in the area is almost always in direct proportion to the number of unemployed. And I'm quite good at drawing people, but I need to practice getting the proportions right. And two of these sentences, the use of the word is in line with the mathematical meaning, and in two of these sentences, it's not. Which ones do you think? Well, in fact, it's in the first two sentences that the word proportion is not in line with the mathematical definition, because the correct word in the first sentence, children make up a large proportion of the world's population. No, it should be fraction. And in the second sentence, the proportion of women to men at my college was about 5 to 1 is an incorrect use of the word by comparison with the maths use, because you should say the ratio of men to women at my college was about 5 to 1. So then the question is, so what, the other two are correct. So then what is the meaning of proportion in mathematics is this. It's an equivalence of ratio. So for example, if we have the ratio 2 to 3 is equal to 4 to 6, these two ratios are in proportion. So it's where we have an equivalence of ratio. And that is the meaning of proportion in maths, strictly speaking. So how does Tirtha use the proportionately sutra? He first uses it in Nicola multiplication when needing to use a working base. So I thought I'd show two examples of how he uses it, and this is the first one. Suppose we have to multiply 54 by 52. We can use a working base of 50 and a real base of 100, where 50 is equal to 100 divided by 2, and the working is shown here. We write down the surpluses of 52 and 54 in relation to the working base 50. So 52 has a surplus of 2 and 54 has a surplus of 4. We then multiply the two surpluses together to give 0, 8. And for the left-hand part of the answer, we cross-multiply 54 add 2 or 52 add 4 gives 56. And then we apply the proportionately rule and divide. What we do to 100 to get to the working base is divide by 2. So that's what we do to the left-hand side of the answer. 56 divided by 2 is 28. And the right-hand side is left alone. Well, I thought we'd just have a look at how this works, why it works, how it works. Why is it that we just divide the left-hand side by 2 and leave the right-hand side alone? So I've done a couple of diagrams to illustrate this. And here we've got a rectangle, and inside it is a shaded rectangle with a base of 54 and a height of 52. And the problem is to find the area of this shaded rectangle. I've also put in the 100 square, as you can see. The little rectangle in the top right-hand corner is the 2 by 4, and its area is 8. And taking the left-hand side of the left-hand part of the answer, 56. That arises if we cross-add from bottom left to top right. 54 add 2. It's actually not 54 add 2, but although that's what happens when you're working mentally, it is really 5400 add 200 because of the place value, and this is 5600. So let's have a look at where that is on the diagram. Again, the light shaded, the light shaded rectangle along the top there has an area of 200. It's 100 wide and 2 units high. The dark shaded rectangle is 54 units wide and 100 units high, and so has an area of 5400. So if we add the dark shaded rectangle here and the light shaded rectangle, we get the 5600. But we only need half of each of those. And that gives us the required area when we add in the little rectangle in the top right-hand corner. So that is an illustration of how the proportionately rule works with Nicolan multiplication. There's another example which I particularly like, is in cubing two-digit numbers. And this is done, here's an example, 12 cubed. This is done by writing down a geometric sequence, starting with the cube of the first digit. The cube of the first digit, 1, is 1. And it takes the ratio, it uses the ratio of the two digits, namely 1 to 2, to generate a geometric sequence of 4 terms. The ratio 1 to 2 just means double. So starting with the first digit 1, which is the cube of the first digit, doubling that 3 times gives 2, 4, and 8. The result of that, at the end, that 8 is the cube of the last digit 2. 2 cubed is 8. The method then tells us to double the inner two numbers, so we get 4 and 8, and then simply add up what we have. And the result is 1728. And this method works for all two-digit numbers when cubing. But why does it work? Why use a geometric sequence here? Well, the answer is found in the binomial theorem, the binomial expansion, rather, of a plus b cubed. You can see here at the bottom the expansion of a plus b cubed. I haven't put in the plus signs there. It's a cubed and then 3a squared b, 3ab squared, and b cubed. Going back to the method for cubing two-digit numbers, if the first digit is a, then the first term in the geometric sequence is a cubed. We then multiply that by the ratio of the two digits. The ratio is b divided by a. And the first term, a cubed, multiplied by this ratio gives us a squared b. And then that multiplied by b over a gives ab squared. And that multiplied by b over a gives b cubed. We then double the inner two numbers and add up. And you can see that that results in the expansion of a plus b cubed. And because a is as a tens with two-digit numbers, the number a is a tens-digit number. That takes care of the place value for the answer. So that is the second example of how tutogy uses proportion. There are lots in the book because it works through a lot of mathematics. And now I'm going to refer back to something I showed in the second webinar, which was the formula for finding the equation of a straight line given the coordinates of 2 points on the line. The form of the equation is ax minus by is c, and what's required is to find the value of the coefficients a, b, and c. The x and y there are the two variables. And if you recall, the coefficient of x is found by subtracting the y coordinates, the difference in the y coordinates. The coefficient of y is found by subtracting the x coordinates. And the independent term c is found using the formula the product of the means minus the product of extremes. So in this case, we set out the coordinates 8, 10, 3, 4, and it's easiest if we put the larger numbers first. Subtracting in the same direction, the difference in the y coordinates is 10 minus 4, giving 6. The difference in the x coordinates is 8 minus 3, giving 5. And then applying the rule, the product of the means minus product of the extremes, 10 times 3 minus 4 times 8 gives minus 2. Then I wondered, okay, what happens when the line passes through the origin like this? So here's a line with 2 points on it, 4, 3, and 8, 6. And if we apply the same formula, of course, we'll get the difference in the y coordinates is 3, the difference in the x coordinates is 4. So the equation will be 3x minus 4y. And then on the right, we find that 3 times 8 minus 4 times 6 is 0. So the independent term is 0. And when looking at the book, the Vedic maths book, there is where he introduces this rule for finding the independent term, product of the means minus the product of the extremes. He says this, and this is with the help of the rule about adyam, antyam, and madhyam. And these words, adyam means first, antyam means last, and madhyam means middle. So the first and the last are the extremes, and the madhyam are the means, the middle numbers. Interestingly, I don't know how this has happened, but the word minus there where he's written, or where it's written, the product of the means minus the product of the extremes, is in italics. And this set me thinking, well, what happens, are there cases where it's equal? And sure enough, yes, as in when the origin, that line in the previous slide goes through the origin, we have the product that means equals the product of the extremes. Now, when you have a ratio, a proportion, like 3 is to 5 as 9 is to 15, you find that the product of the middle two numbers, 5 times 9, is the same as the product of the outer two numbers. 3 times 15, both give 45. And from this, we can utilize this for solving ratio equations. So we've got this rule now, the product of the means equals the product of the extremes. And it turns out to be very useful. We can use it for solving ratio equations. So suppose we've got 3 is to x as 22 is to 66. Yes, it's possible, if you are numerate, it's possible to solve this ratio equation at sight, just by noticing that 66 is 3 times 22. And so the answer must be 9. But if you're not that numerate, you can follow the formula and say the product of the middle two numbers, 22 times x, is equal to the product of the outer two numbers, 3 times 66, and solve it to give 9. And this rule can be applied to all ratio equations and problems. For example, Mrs. Baker has a pie recipe that serves 6 and uses 280 grams of flour. How many grams of flour does she need to serve 9 people? So that's a typical problem for 11 or 12-year-olds in proportion. We can set down the ratio like this. 6 people is to 9 people, as 280 grams is to x. That's nice and clear. And then we can use the formula. 9 times 280 is 6 times x. And then solving that gives 420 grams. Here's a harder problem with percentages. Find the percentage loss when a bicycle costing £480 is sold for £320. It's quite an expensive bicycle. So here's one method. We can set down the 480 is to 320 as 100 is to x. And that x there is not the percentage loss, but is the percentage of the original cost that the bike is sold for. So we have to do a subtraction afterwards. But setting out the ratio equation, we can use the formula to solve it, arriving at 66 2/3%, which means that £320 is 66 2/3% of 480. So the percentage loss will be 100% minus that, which leaves 33 1/3. Another method is just to go directly for the loss, which is £160, and then apply that to in the formula. £160 is to 480 as x is to 100, and that arrives at the same answer of 33 1/3, a bit more directly. So now there's another area that this rule can be useful, I've found, in teaching quadratic equations, in factorizing quadratics rather. So and this is where the coefficient of x squared is more than 1, which are the harder type. In the Vedic maths, we're taught to set out a ratio equation like this, using the first coefficient and the last coefficient as the outer two numbers. So we're looking for two numbers here that fit into this ratio, this proportion. 3 is to something as something is to 8. And the two somethings we're looking for must add up to 10. Well, this one's fairly easy. We can see it's got to be 4 and 6. It doesn't matter which way round you write the 4 and the 6, but that's the proportion. We then take one of those ratios in lowest terms and use that for the coefficients of the first bracket, 3x plus 4. We then take the first term of the quadratic and the first term of the bracket found so far and divide 3x squared divided by 3x, and the last by the last, 8 divided by 4, to give the two numbers for the second binomial. And that's with this subsutra, the first by the first and the last by the last, x plus 2. A slightly harder example is shown here, 2x squared minus 9x plus 10, where we've got a minus sign involved. And when we're looking for the two numbers, 2 is to something as something is to 10, they've both got to add up to minus 9. And after searching around a bit, we will find minus 4 and minus 5 fit in there. We take either one of those ratios and reduce it to lowest terms, and that gives the coefficients for the first bracket, 1x minus 2. And then by division, 2x squared divided by x gives 2x, and the last by the last is 10 divided by minus 2 is minus 5. And now a harder example, 6x squared minus 7x minus 24. And with practice, I find children can get the easy ones, but when faced with something a bit harder like this, they get stuck. So this is where our formula, the product of the means equals the product of the extremes, can rescue us and get us out of this tricky problem. Because 6 times minus 24 has got to be the same as the product of the middle two numbers. So the two numbers we're looking for, have to multiply A and B. They have to multiply together to make minus 144. That's 6 times minus 24. And they have to add up to make minus 7. So now we're looking for two numbers whose sum is minus 7 and whose product is minus 144. And 16 and 9 are involved there. If this works, yes. 6 is to 9 as minus 16 is to minus 24. So the formula has helped us solve this or factorize this quadratic. We also find a proportion used in a lot of geometry problems. So I just thought I'd illustrate one problem where it is used. So have a think about this problem. A triangle has two sides divided into 4 equal segments, and lines parallel to the base are drawn so that the triangle is divided into 4 sections. And the question is, what fraction of the whole is shaded? I'll give you a few seconds to think about that. In the diagram, we've actually got 4 triangles, and they are all similar. So they are in proportion. The solution to this problem is remarkably easy if these following lines are drawn. Here I've divided the triangle up with lines parallel to the sides, and all the small triangles shown are the same as each other, and there are 16 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, of which 10 are shaded, and so the answer is 5/8. Sort of problem that looks hard at first, but it's nice that there's an easy solution to it. And we also find proportion is used is used very much in the world of design, both in the natural world and in the man-made world, so to speak. Particularly well-known proportion ratios like the golden ratio. And interestingly, I came across some website talking about the design of the use of the golden ratio in design, and quite remarkably, all these well-known symbols for cars. What have we got here? We've got Honda, Mazda is top left, isn't it? Mercedes, Honda, and Toyota. They all use the golden ratio. And these diagrams show it in the way. For example, the Mazda one, top left, has two golden rectangles sitting next to each other, and is based on that proportion. Here is another very well-known logo using the golden rectangle, which is full of this ratio. There was a Roman engineer, architect, who lived at the same time as Julius Caesar, roundabout, and he was very famous in his own way, Vitruvius, who said that proportion is that agreeable harmony between the several parts of a building, which is the result of a just and regular agreement of them with each other, the height to the width, this to the length, and each of these to the whole. And I thought that was quite a nice description of the way in which proportion is used in buildings. Proportion is an agreeable harmony. I very much like that description. And here is an example of the proportions used in a famous building. Of course, this is the Taj Mahal, analyzed with all its geometry. And here's another example of proportion being used. This is a pagoda in Bali. And a very famous example from ancient Greece, this is the Parthenon, which is full of the golden ratio as well. And the building has most agreeable ratios and proportions in it. There was a French monk in the medieval times who said this about proportion. He said, since this monk, it was called Saint Bonaventure. He's a Frenchman. He was a Frenchman. He said, since therefore all things are beautiful and to some measure pleasing, and since there is no beauty and pleasure without proportion, and proportion is to be found primarily in numbers, all things must have numerical proportion. And while we learn that things have numerical proportion, we take pleasure in this numerical proportion, and we judge things irrefutably by virtue of the laws that govern it. So I thought that was also a very lovely description of how proportion relates to beauty, because these buildings and designs that we've just been having a look at are beautiful and are full of harmonious ratios, which are proportion. So I think we'll end there. Oh, just one extra slide is to show some of this, how beautiful proportion works in nature. And here it is. This is the giant nautilus shell cut in half, showing all the segments.